Hello, GH101. Here we're going to do part 2 of looking through Harvard CSP's Computers and Computing, part 1 and part 2. So we've already done part 1, that was reviewed. Now part 2 we're going to do new stuff. We did not keep track of quiz 3 terms, we'll put that in later. And I'm going to use our slides and pictures to do some examples. Alright, so we can keep track of some things over here. Binary, yippee-doo. So we keep notes over here. Here we have binary. Alright, so the information that we need to know about binary is binary is base 2. Note that normal numbers are base 10. Okay. Alright, see slides for examples. I'll put more over here. So we have alright, so a base 10 number. So a base 10 number, we have something like 293. Alright, so if we have that number, then we say that the 3 is the ones digit. What is the 9 called? The tens digit. And what is the 2 called? Hundreds digit. Okay, so another way to write this number, 293, is 2 times 100 plus, put it like this, 3 times 10 plus, sorry, 9 times 10, 3 times 1. All right, and there we see the 3 is the ones digit, the 9 is the tens digit, and the 2 is the 100s digit. Another way to write this is 2 times a power of 10. So what power of 10 is 100? And I want to make this look good, so superscript. All right. 100 is 10 squared, and then plus 9 times 10 to what power? 1. And then plus 3 times what power of 10? 0. All right, 10 to the 0 is 1. All right, let's try this again. Write, let's say, the number 4702. All right, so write that in terms of powers of 10 like this. So I'm pausing. So pause so you can do that. All right, and now I'll show you. So 4 is the thousands digit. That's 4 times 10 cubed. 7 is the hundreds digit. That's 10 squared. We have a tens digit. It happens to be 0. And then we have a 2. 2 is the ones digit. So we see that when we write numbers like this, what we really mean is each digit is multiplied by 1 greater power of 10. Okay? And so we just assume that. We get taught that in elementary school, and it just is in our brain. It just is, it's just there. But 10 is not there's nothing super special about 10 other than the fact that we have 10 fingers, or most people have 10 fingers. We could have used any other multiplier here. All right, so I'm going to give you another one. So what would happen if we try to do this, but instead of 10, we put 8 in? Okay. So my first example, 293, we can't do this. So what I mean by base 8 number is, so the rules will be, we have the digits are 0, 1, 2, 3, 4, 5, 6, and 7. There's 8 of them. All right, so there's 8 digits. So you're up to 7. And we do powers of 8. Okay, so we'll note that 293 is not a base 8 number. We can't think of it as a base 8 number because that 9 is not allowed. Let's look at our example 4702. What if we think of this, instead of thinking of it as powers of 10, what if we do powers of 8? Okay, so 4 times 8 to some power. I'll just put a blank there for now. Plus 7 times 8 to some power. Plus 0 times 8 to some power. Plus 3 times 8 to some power. All right, and when we're doing base 10, we start with the power of 10 to the 0, that's the ones. Then we have 10 to the 1 power, and then we have 10 squared, and then we have 10 cubed, and we do the same thing for other base systems. So we start with 10 to the 0, which is the same as saying 1. Then we have, 8 to the 0, and then we have the 8th digit. And then we have the 8 squared digit and the 8 cubed digit. All right. We could multiply this all out. 4 times, what is 8 cubed? Anybody know offhand? 8 times 8 times 8 is 512. Plus 7 times 8 squared is 64, plus 0 times 8, plus 3 times 1. All right, so what is that? That's something we can put into our calculator or ask Google. 2,499. And I'm going to put a little let's see, I want to make this a subscript. Okay. This is not, so I have to do it this way. All right, so I want to put a 10 there and put a 8 here. So if I'm thinking of this as in base 8, then in base 10, that's equal to this. All right, if we want to do some other ones, we could find a base 8 calculator. All right, so what did I have? 4702. Sorry, 4702. Oh, 03. All right. All right, and here's some easier ones. All right, so maybe you want to pause and pretend you're confused, but let's do a few easier ones. Let's say that we have the number 7 in base 8. What does that equal in base 10? Just 7. We'll do it like this. Okay. Now what about the number 10 base 8? What does that equal in base 10? Well, you'd be doing this, except your digits would be 1 and 0. You have 0 times 1 and 1 times 8. So that's 8. How about the number 20 base 8? Well, your 2 is multiplied by 8. So that's 16. Okay? So we're calling this now, we didn't do binary here, we did base 8, which is called octal. Now let's go for binary. We play the same game, but we're going to use 2 instead of 8. Okay, so we want to do, this is base 2, called binary. All right, we want to have our digits that are allowed. We only want 2 of them, so 0 and 1, that's it. So we're allowing 0 and 1, that's 2 different digits. And then if we, so those are the only ones allowed. If we have a number like 1100, something like 234, not a binary number because we're only allowed to have zeros and ones in the number. Let's say we have a number like this, okay, and I'll put a 2 next to it, subscript 2, just to remind us that we're talking about thinking of these as base 2. All right, so we're going to do the same thing we did with the powers of 8. So here we had this 3 was the 1's digit, the 0 was the 8's digit, 7 was the 8 squared, and the 4 was the 8 cubed. So we'll do the same thing where we have 1 times a power of 2 plus 1 times a power, the next power of 2 plus 0 times the next power of 2 plus 1 times. All right, so we have 2 to the 0, this is the 1's digit, this is the 2's digit, this is the 4's digit, this is the 8's digit, or the 2 cubed. And then we just multiply by all this out. We have 8 plus 4 plus 0 plus 1, which is 13 in base 10. Okay, let's try another easy one. Let's say we have the number 1, 1 in base 2. What is that as a base 10 number? So pause, say what you think it is. Okay, now, so we're looking at a base 2 number. This is the 1's digit. This is the 2's digit. So we have 1 times 2 plus 1 times 1 is 3. How about 101? If we take that as a binary number, that's 1 times something plus 0 times something plus 1 times something. And you go, this is the 1's digit, this is the 2's digit, this is the next power of 2, which is 4. So we've got this is 5. Okay, So we can take a number that's binary, that's just bits, ones and zeros, and convert that into a decimal number. I think we'll call that it for now. And so then the next video we want to say, can we go the other way? So how to convert a number like, I don't know, 23 from decimal to binary. All right, so we'll do that in another video. Why do we care about this? We'll see pretty soon how this can be useful in terms of looking at things on the computer. The not answer for why we're interested in this is because computers talk in binary. Everything in the computer is either on or off, a 1 or a 0, and so it happens that we need to look at the actual bits of the data. So the data in the computer really is stored as ones and zeros. All right, so you should be able to convert a number from base 2 into decimal. You should be able to convert a number from base 8, which is called octal, into decimal. The end.